Today's lesson, we're going to discuss section 15.3, independence of path and conservative vector fields. So first, let's remind ourselves about the work integral that we've seen previously. If F is a force field in R2 or R3, then the work performed by the field on the particle moving along a parametric curve C from an initial point P to an initial point or to a final point Q is given by the integral work, or W, equals the line integral over C of F dot dr. We call an integral of this type a work integral, and the parametric curve C in a work integral is called the path of integration. By the name of this section, you can assume that we're going to be working with these work integrals, but specifically, we'd like to understand when the path of integration is less important. In particular, when can we assume that this work is independent of path, and how can we determine that? So again, our goal is to determine whether a line integral can be computed independent of the path of integration. All right, so before we get there, we need to understand something called conservative vector fields. So we say a vector field F in R2 or R3 is said to be conservative in a region if it is the gradient field for some function phi in that region. That is, F equals the gradient of phi. So this is going to be a very important equation here. The function phi is called a potential function for F in the region. I just want to point out at this moment that this concept of conservative vector fields and potential functions is going to be very important once we move into differential equations for those of you taking that next semester. In particular, we're going to use this entire process that we're learning in this section when we talk about what's called exact equations in differential equation. So I just want you to kind of keep that in the back of your mind that this entire section is going to pop back up and play a big role next semester. All right, so how can we check if a vector field is conservative? That brings us to theorem 3. If f of x, y, and g of x, y are continuous and have continuous first partial derivatives, and if the vector field is composed by f in the I hat and g in the j hat is conservative on D, then we need only check that the partial of f with respect to y is equal to the partial of g with respect to x at each point in D. Conversely, if D is simply connected and the above equation holds at each point, then we say that f is conservative. All right, so we're going to use this equality of the partials to check for conservative fields. So here's how we're going to go about finding a potential function. First, check that your vector field is conservative by checking those partial derivatives. Next, we're going to set up partial derivatives of phi. And so I just want to emphasize where these are coming from. Let me scroll up again. Remember this equation that f is the gradient of phi. So if we take a look at that here, let me rewrite that equation. F is the gradient of phi. Well, what that means is that the partial with respect to x of phi is in the I hat component, and the partial with respect to y of phi is in the j hat component. But remember, let me grab a different color here. This I hat component is assumed to be given by little f, and the j hat component is assumed to be given by little g. And so you'll notice that we're just equating those two pieces together here. All right. So the first component function is the partial of phi with respect to x, and similarly for y. So now we have these two equations, 1, 2. We can choose to work with either one, and generally speaking, I just work with the first equation for no particular reason. And I'm going to say, all right, how can I undo this partial derivative with respect to x? I can undo it by taking the partial integral with respect to x. And so that's going to leave me here with phi of xy rather than partial phi partial x. Now, you'll notice this extra piece here on back. Normally, when we're integrating a single variable integral, we tack on a plus c for our constant of integration. However, I want to emphasize that this is not a single variable integral now. This is a multivariable integral, and we're only integrating with respect to one of those variables. So instead of a constant of integration, since we're integrating with respect to x, my my constant of integration could now be a function in y, because in the eyes of the partial integral with respect to x, anything strictly in terms of y is itself a constant. So to be extra careful, I'm going to write this constant of integration as k of y. Now, it may turn out to be a constant after all, but it also could be an expression in y. So to be safe, we're going to write it as such. So this is kind of our first attempt at finding phi of xy. So I'm going to note that first attempt at phi of xy. All right, but what is that constant? So what is k of y? We're not satisfied with leaving our phi of xy in terms of some k of y function. So what we're going to do is we're going to use equation 2, which we have yet to utilize, in order to kind of flush out what that k of y function must be. So to get to that second equation, what I'm going to do now is I'm going to differentiate with respect to y. So I'm going to take this, I'm going to take this integral that I just found, whatever it was in that previous step, and I'm going to take its partial with respect to y. And that's truly what this left-hand side is. Now this right-hand side, again, let me grab a different color. This right-hand side is saying, look, I already set up this equation where the partial with respect to y is equal to g of y. So that's where the the right-hand side of this equation is coming from. This should leave us with a single equation, typically in one variable, and then we're going to use this to solve for this missing piece k of y. Once we've found that, we've kind of unlocked the mystery for phi of xy, and we should at this point have a full equation for phi of xy, no longer involving a k of y, but this time only involving some constant of integration. All right, so let's practice working with these functions and solving for potential functions. So the next page here is just going to be working with vector fields, checking whether they're conservative, and if they're conservative, solving for this potential function. So let's get started here with problem number 2. We have a given vector field, and what I'm going to do first is I'm going to take the partial with respect to x of f. So that is partial with respect to, I don't want with respect to x. I want with respect to y. So we'll correct that. So I'm going to take the partial with respect to y of 3y squared, and that equals 6y. Let's also find the partial with respect to x of g. So that is the partial of 6xy, which gives me 6y. All right, so at this point, I confirmed that this is a conservative vector field. All right, so now I would like to move forward in finding the potential function. As I mentioned previously, I'm going to work with this first equation rather than the second equation. And I'm going to say, how can I undo the partial? All right, so let me set up my equations. I'm going to say the partial with respect to x of phi is 3y squared, and the partial with respect to y of phi is 6xy. So let me rather label these 1 and 2. So working with this first equation, I'm going to say if I want to undo the partial with respect to x so that I recover phi of xy, I'm going to take the partial integral of 3y squared with respect to x. All right, so as it's written, this integrand doesn't have any x's in it. When I integrate it, I'm just going to tack an x on. And then instead of a plus c for my constant of integration, since this is a multivariable integral, I could have had some quote, quote, constant of integration that would have been with respect to y. So I'll write it like this. All right, so the question remains, what is this constant k of y? So now what I'm going to do is I'm going to take the partial derivative with respect to y of this phi function. So I'll write that as 3xy squared plus k of y. I'm going to take its partial, and that is 6xy plus some k prime of y. I don't know what that function is, but it's a function of y. And then I'm going to look back up at my equation 2, and I'm going to say, oh, okay, this is the partial of phi with respect to y. And so I'm going to equate it to 6xy. So what I see in this example is I have 6xy on both sides of the equation. This means that k prime of y is equal to 0. And this has resulted in a single variable equation. If I just integrate both sides with respect to y, that gives me that k of y is equal to 0 plus c, right? The integral of 0 is just our constant of integration. So now I'm going to take this value for k of y and I'm going to plug it back up here into my phi of y equation, phi of xy rather. And so I conclude that my potential function phi of xy is 3xy squared plus some constant of integration. So I'm going to box this in. This is my final answer. All right, so there's several steps here and you're working back and forth between what I've labeled as equation 1 and equation 2. So make sure you're feeling comfortable with how we're using both of them and the interplay between both of them to really flush out that k of y constant of integration. Let's take a look at problem number 4 as well. First, let's check to see if it's conservative. So I'm going to compute the partial of f with respect to y. So that's the partial with respect to y of e to the x cosine y. The derivative of cosine is negative sine. So this is a negative e to the x sine of y. I also want to compute the partial of g with respect to x. So that's the partial with respect to x of negative e to the x sine y. The derivative of e to the x is itself. So this just remains a negative e to the x sine y. So again, I have confirmed that this is a conservative vector field. At this point, I can move forward with finding a potential function. So I'll set up my two equations. One is that the partial of phi with respect to x is the first component function. And the second equation is that the partial of phi with respect to y is the second component function. Okay, so again, it's arbitrary which one of these equations you want to work with first. I typically work with equation 1. So I'm going to say, well, I would like to recover phi. How can I undo the partial derivative with respect to x? And so to undo that, I'm going to take the partial integral with respect to x. All right. And so tack on my dx to indicate that I'm taking that integral with respect to x. Cosine of y is a constant in the eyes of this integral, and the integral of e to the x is itself. So I get e to the x cosine y plus my constant of integration, which in this case is some k of y. So now I want to take the partial of phi with respect to y. And so I'm taking the derivative of e to the x cosine y plus k of y. And so that's going to leave me with a negative e to the x sine of y plus some k prime of y. Again, I'm going to come back up top and say, well, phi sub y is given by this equation boxed in red, negative e to the x sine of y. So this is how I'm utilizing the information that I get from equation 2. Here again, we're seeing this duplication of this factor here on the left and the right. I want to emphasize this will not always be the case that k prime of y equals 0. It just is in these examples. So on the very next page, we're going to see an example where k prime of y is something more interesting than 0. So now again, if I integrate both sides with respect to y, I get that k of y equals some constant of integration. And finally, I want to take this value for k of y and I want to plug it, whoops, I want to plug it back up into my phi of y formula for k of y. And so here, my final answer for my potential function phi of xy is e to the x cosine y plus a constant of integration. All right, let's take a look at the last example here on this page, number 6. First, let's check to see that this vector field is conservative. So I want to identify the partial derivative with respect to y of f. So that is partial y of x natural log y, which is x times 1 over y or x over y. Let's also compute the partial with respect to x of g, which is partial x of y natural log x. This is y times 1 over x, which is y over x. You'll notice that these are not equal. And so we conclude that this vector field is not conservative. So at this point, you can stop on this problem. There is no sense in trying to recover a potential function because those potential functions only exist if you're working with a conservative vector field, which this one is not. All right, so what do these potential functions have to do with line integrals? Because so far we haven't seen how they relate to that work integral. And so we have what's called the fundamental theorem of line integrals. It says, suppose you have a conservative vector field, and we're going to call those component functions little f and little g, on some open region containing the points x0, y0, and x1, y1. And suppose that the component functions f and g are continuous on the region. If you can express this vector field as the gradient of a potential function, which we've just been practicing, and if C is any piecewise smooth parametric curve that begins at x0, y0, and ends at x1, y1, then we say that this line integral, f dot dr over C, we can rewrite that as the line integral of the gradient of the potential function dot dr and the integral of the gradient of the potential function. That integral and gradient just undoes each other. And what we get is we just want to evaluate the potential function at the endpoint minus the potential function at the beginning point. And so what this is telling us is we really don't care about that path of integration. That parametric curve C really doesn't matter. All that matters is the beginning of the curve of integration and the ending. So this is where we're seeing this independence of path, all right? What's happening in between is irrelevant, and we only care what's happening at the beginning and end point. All right, so let's utilize this theorem here to solve this line integral. You'll notice there's a huge hint that this is going to be using the fundamental theorem of line integrals because instead of giving us a parametric curve here, they only give us endpoints. So this is indicative of the fact that this vector field is going to be conservative and we're going to use this independence of path. So first, let's check to see that this is conservative. So first, I'm going to take the partial with respect to y of my f component function. So this is partial y of 3x minus y plus 1, and that gives me a negative 1. Let's also compute the partial with respect to x of g. So that's the partial f, or partial x of, and actually, what I'm going to do first here, and let me write this in red to call your attention, I'm going to distribute this negative here so that it becomes a plus inside. So that being said, let me write this as negative x minus 4y minus 2. So now when I take this partial, obviously these go to 0 and I just get out a negative 1. All right, so at this point, I have determined that this is a conservative vector field. I can move forward with finding a potential function. So let's set up our first two equations. The one is that the partial of phi with respect to x is the first component function. And the second is that the partial of phi with respect to y is the second component function. Again, I'm being careful to just distribute that negative right out of the gates. All right, so working with the first function, I am going to make my first attempt at recovering phi of xy by integrating with respect to x. All right, so integrating each of these summands with respect to x gives me a 3/2 x squared minus xy plus x. And then again, instead of a plus c, since this is a multivariable function in x and y, I'm going to write my constant of integration as some k of y. So now the question is, what is k of y? Can we do better than just writing some arbitrary function there? So now I'm going to take the partial with respect to y of this phi function. So I'm going to rewrite what I just found. All right, and we can see here that a couple of these pieces are going to go to 0. And so all that will remain is a negative x plus k prime of y. And now what I'm going to do is I'm going to equate this with what I had previously set up for phi sub y. So maybe over here in the margin, I'll write phi sub y. All right, so this is equal to negative x minus 4y minus 2. So we see cancellation here of the negative x's, but finally we have something more interesting for k prime of y. It's not just equaling 0. So k prime of y is negative 4y minus 2. You'll notice that this entire equation is single variable, only with respect to the y variable. So I'm going to take the integral with respect to y on both sides. to recover k of y. So k of y is going to be a negative 2y squared minus 2y plus c. So now let's take this expression for k of y and let's plug it in for our phi function. So now our phi function, or our potential function, is 3 halves x squared minus xy plus x minus 2y squared minus 2y plus c. All right, so we have a full function for phi, and now we would like to compute this line integral. Since we just determined that it was conservative and independent of path, what I can do now is I can take this line integral from negative 1, 2 to 0, 1, and I'll just rewrite out my integrand. And according to the fundamental theorem of line integrals, this can just be found by evaluating my potential function at the upper and lower endpoints. So this is phi of 0, 1 minus phi of negative 1, 2. So let me compute those values here just kind of separately. So phi of 0, 1 is going to give me 0 minus 0 plus 0 minus 2 minus 2 plus c. So negative 4 plus c. And phi of negative 1, 2 is going to give me 3 halves plus 2 minus 1 minus 8 minus 4 plus c. All right, so let's see what that is. All of these whole numbers, negative 13 plus 2 is negative 11. So negative 11 is negative 22 over 2 plus 3 over 2 gives me a negative 19 over 2 plus c. All right, and so finally, coming back to my line integral, I have phi of 0, 1 minus phi of negative 1, 2 is negative 4 plus c minus a negative 19 halves plus c. You'll notice that those constants of integration are going to cancel. And so what I have here is negative 8 over 2 plus 19 over 2 for a final answer of 11 over 2. All right, so we get 11 over 2 units for this line integral. All right, so we have one more example here to finish off the section. We're going to come back to our roots here with work done. So first we want to confirm that our vector field is conservative, and then find the work done by the force field on a particle moving from P to Q. So this is our initial and terminal point of motion. All right, so let's begin by checking for conservativeness. I'm going to find the partial of f with respect to y. So that is the partial of 2xy cubed. And that's going to give me a 6xy squared. And let's also take the partial of g with respect to x. So that's the partial of 3x squared y squared, which is 6xy squared. So this proves that we're conservative. Okay, so next let's go ahead and find our potential function. I'm going to set up my two equations. Phi sub x is the first component function, and phi sub y is our second component function. And now I'll work with the first equation. Our first attempt at solving for phi of xy is by undoing the partial derivative with respect to x. Okay, so I have this dx. And so when I take this integral, I'm going to get an x squared y cubed, and then plus my constant of integration. So now I'm going to say, all right, I'd like to use that second equation. So let's take the partial with respect to y of the function that I just found. So that's going to give me a 3x squared y squared plus k prime of y. And here's where I'm going to equate that with what I have for phi sub y. Right, so here's another example where our k prime is boring. So I get that k prime of y equals 0. So if I integrate both sides, k of y equals some constant. So I will now take this constant and plug it into my phi of xy formula. So phi of xy is x squared y cubed plus some constant of integration. Kind of a boring potential function here. So now my goal is to find the work, which is the line integral. In this case, since it's conservative, I only care about the endpoint. So I have my initial point at bottom, my terminal point at end of f dot dr. But I won't even bother writing all of that in. We can forego going through the actual line integral like we learned in 15.2, and instead we can evaluate our potential function at these endpoints. All right, so this becomes 16 times 1 plus c minus 9 times 0 plus c. Our c's cancel, and so we get 16 units of work is completed by this vector field on a particle moving from P to Q. That's all for today.